Okay, so this is my review of my practice test for test 2. Like I said, this will be uploaded on Tuesday. So try and focus on understanding concept and like how math can relate to it, use that to rationalize. I have book problems on my WordPress site, so just continue to go over those. And this will be divided up into several parts because YouTube doesn't let me post more than 15 minutes, but that's a-okay. So, all right, write the expression for the rate of change for the following equation, 2a plus 3b to c plus 4d. So, well, yeah, ignore that. It just didn't transfer right. So when it asks you for like the rate of change, that's not the same as the rate law. This is just, the rate of change is just sort of, it is how concentration is changing over time, but it doesn't take into consideration the effect that order has on it. So when you write it, it's essentially saying like, let's say for every 0.2 molar that this decreases per 10 seconds, this decreases by 0.3 molar, this increases by like 0.1 for example, and this increases by 0.4. So you have to take into consideration that their rates are not equal because of those coefficients. Well, I say their rates, but like because of the coefficients, they're not inherently equal. So you write this rate of change equation to make them on equal footing. So it'll be something like rate equals, and then you have to divide by the coefficient. And because A is disappearing, it's going to be negative, right? Because it's a reactant and it's forming a product. 1 over 2 times change in A over T. And that's a change right there. I'm going to go ahead and erase that. Well, that was dumb. So it's 2A plus 3B to form C plus 4D. Alright, so same here, it's going to be equal to negative 1/3 change in B over delta T. And because these are appearing, it's going to be positive, so this is just going to be delta C over delta T. And look at that coefficient, that's a 4, so 1 over 4 times delta D over delta T. So that's the expression for the rate of change, right? So number 2 is when you start having, the relationship between order and the rate of reaction. So I just think it's helpful to write out the rate law, which is rate equals K times A, to the X, and like B to the Y, right? And when these are our orders, and these orders are going to tell us how our change in concentration affects the rate. So 0, 1, and 2. If I raise something to the 0, so anything to the 0 is going to be equal to 1, right? Raise 1 to the 0, that's 1. Raise 2 to the 0, that's 1. So when it comes with respect to order, if let's say I double this concentration for something that's 0 order, that tells me that there's no effect on rate. So concentration has no effect on rate. All right, so if something is first order, let's say I raise 2 to the 1, or that's 2. If I raise 3 to the 1, that's 3. So that tells me that if I double my concentration, I will double my rate. So to synthesize that shorter, my rate is going to be directly proportional to concentration. And that's the same, let's say if I halve it, let's say I have my concentration, I'm going to halve my rate. And I just use the brackets for concentration. So if something is second order, that means, let's say if I double my concentration, I'm going to quadruple my rate. Let's say if I triple my concentration, my rate is multiplied by 9. So essentially, these, the reaction is really sensitive to changes in concentration of something that's second order. So rate is proportional to the square. That's how I like to synthesize it. So I'll just put like concentration squared. So similarly, let's say I have my concentration, right? I still have to raise that to the second. That means my rate is going to decrease by a factor of 4. It's going to be 1/4 of what it originally was. So keep in mind there that, squaring exponents and fractions. Well, squaring exponents, squaring fractions. So just be aware of that. So number 3, how is the order of a reaction measured? So you want to do this experimentally. This isn't really just like a trick question, but I've seen it asked on tests. So I want to measure experimentally, and you do that with those little tables, right? Where it has like rate, and that's concentration, and then it has the different concentrations that you have, right? So for something like this, what you want to essentially do, hold on. Uno momento. I don't know why I'm doing all of this. So when I have, like let's say these rates and these concentrations, and I'm trying to find the order of reaction, I want to look, so if I want to find the order, I want to look at where only one reaction would be affecting the rate. So that'd be where one is changing and the other is not. So for example, like in my little like pseudo diagram, this stays at 1, whereas this is halved, right? And so I want to look at how the rate changes. Like let's say if I had a rate of 4 right here and then it goes to 2, well, I halved this concentration and this halved as well. So that's how I'm going to know that that's going to be something that is first order, because it's directly proportional. So similarly, if I want to find it for the other reactant, i.e. let's say this one, I'm going to want to look where the one on the left stays the same and this one changes. So that would be the second and third lines of data. So let's say it goes from 2 to 2. I double my concentration and the rate stays at 2. That tells me that it's 0 order, right? Because it didn't matter that I doubled it, my rate stayed the same. So that's essentially how you want to look at it. I do it a shorthand way like that. You can also write it out like in divide rates, or it's like rate over rate equals K times whatever that concentration is, and then like their orders, right? So if one's staying the same, like if this is staying at 1, then that's going to cancel out. The K's will cancel out. Let's say I have something like that. Then that's just going to be 2 to the x equals whatever these rates are over here divided. So if you don't like to do it based off the chart and you like to have it like written out, I would practice that method. What is meant by the term half-life? Okay, this is about like very important. So this is just the time to get to 1/2 the original concentration. So I'll just write AO, right? So it's important because students tend to want to go directly to the half-life equations when you should be using the integrated rate laws. So when I use the integrated rate laws, I think they're important to know because they're fun. That's a lie, they're not fun, but I tried. So AT equals negative KT plus AO. These are integrated rate laws, not the half-life equations, right? And then this one is ln of AT equals negative KT plus AO, or ln AO. And this last one is 1 over AO equals KT plus 1 over AT, 1 over AO. So important things to notice here, or like take away from the integrated rate laws, is one, I'm going to use them when problem asks for like how the change in concentration over time changes, how long it takes to go from this concentration to this concentration, and it may even ask you about plots where it gives you like, oh, a plot of ln of AT over time is linear with a slope of this, like a slope of, I don't know, -2, right? Oh. So important things to take away there, it would ask about the order. If it says a plot of ln of AT over time, that means that my ln of AT is my y-axis, and this equation essentially looks like that y equals mx plus b, right? So I would know that if something has a y-axis of ln of AT and it's linear, that it's going to be something that's first order, that reaction is first order. If it gives me a slope of -2, I know that that -2 is going to be equal to -k, right? Because that's my m right there. And there's my x, which is t, and then this ln of AT is my y-intercept. So you should just be able to differentiate the units here and just know from there that when it gives you the slope, it's referring to k. Important thing to note here is that the k for something that's second order is going to be positive, so don't let that throw you off. if you're trying to differentiate, like if you can't remember the units, but I would just try and remember the units. It'll help out a lot. So let's see, I'm going to do one more and then I'm going to pause because I have an SI session. So the term activation energy is essentially just the energy required to like jumpstart the reaction. So let's say if I have something like this is like energy, this is the progress, I'm just going to write prog, that's cute. So the takeaways here are just to be able to like sort of analyze and like understand what's happening. So I'm going to see if I can zoom in a little bit more. So let's say, let me make this smaller. This right here is going to be my activation energy. That's my activation energy. Once I reach this threshold, then the reaction for sure is going to happen. So I start over here with reactants and I end over here with products, right? And this is my transition state where, you know, there's sort of some bonds formed, whatever. Another important thing to note here is this, so basically between the initial and the final, that's my delta E. That's the change in energy. This is not, so like this little area right here is not my delta E, that's my AE. That's the energy required to, or I guess EA, whatever they like to say it is. EA, whatever makes you feel better. So what you would want to look at and differentiate between these two graphs is look at the activation energies of the one on the left and the one on the right. The one on the left has a much higher activation energy, meaning that it's going to be a slower reaction. The one on the right is much smaller, it doesn't take enough as much energy to perform. Beyond that, just review the book and just make sure you can understand what's going on with these. I think it's really fun. All right, I'm going to pause here because I have an SI session.